systems of equations in Cartesian coordinates, where you use substitution or elimination or other clever techniques to solve for x and y and, figure out the intersection points of equations. Well, we also wanted to be able to do that for polar equations as well. So we're going to go through and look at 5 different ways that you can solve polar equations. Now, polar equations are a little bit trickier in some ways because in Cartesian, when you solve a system of equations, you always get all the solutions. For polar, that's not true because of some of the quirks of how polar works. Okay, so let's look at some examples. Okay, so the first one we're going to look at, we're just going to say, what if we just have a basic system? So let's say we have r equals 1 and r equals 2 cos theta. And I want to figure out where these two things intersect. Well, what I can do is, for all of these methods, no matter what, always try to start out with a sketch if you can. Okay, so this one we definitely can because I have a circle of radius 1. And then I have a circle that passes through the pole. Okay, so if I have a circle that passes through the pole, 2 cos theta, I'm going to have this. And I'm going to have 2 intersection points. Now, there are other ways I could do this, right? I could have instead so I have this and I could have that. Then I have 0 intersection points. Or I could have this and then I could have that, right? So then I have 1 intersection point. So I could have 1, 0, or 2 intersection points. But having a sense, right, this is a circle with diameter 2, so I actually know for a fact that, okay, this distance is 1, this distance is 1, its center is actually here, so it has to have 2 intersection points because I can sketch this pretty accurately since I know what this equation means, okay? So when we're solving systems of polar equations, we're really going to be pulling from limacons, from circles, from all the stuff that we've done so far with polar, okay? Which is why I can sketch this and say, okay, it's not going to be one of these, I'm going to have 2 intersection points. And for this one, there's nothing really too tricky about this. All you do is say 2 cos theta equals 1, just like you guys have done in the past, and you solve this. You say cos theta equals 1/2, which means theta is going to be equal to pi over 3, or 5 pi over 3. And I stop there because when we're solving this, and this is a thing I should really note at the top, is we're always going to say that theta is between 0 and 2 pi. Okay, because yeah, we can represent this intersection point and this intersection point in an infinite number of ways, but who cares? Like, we just want to know where they intersect, and that's it. So this is sufficient. That's all we need. So that's our theta. But what about our r? Well, for this one, r is 1. I take these, plug it back in. Now you plug it into this one, you just get r is 1. You plug it into this one, and you get 2 times cos of that is 1/2. So 2 times 1/2 is 1. You get the same thing. Which means our points, our answer, I guess I shouldn't really have boxed that, right? Our answer is going to actually be 1 pi over 3 and 1 5 pi over 3. Okay, so those are our answers, our intersection points here for just a basic system. Okay. Next one we're going to look at is going to be kind of similar to this, with one small difference. So this one I'm going to call use the graph. Now, like I said, we always want to graph it, and we always kind of want to use the graph to determine intersection points, or how many intersection points there's going to be if we can. But for this, we really have to use the graph. Because what we're going to have is we're going to have r equals cos theta, and we're going to have r equals 1 minus cos theta. So this is a circle that passes through the pole. This is a cardioid, right? Because a over b is 1. So if I graph this, then what I'm going to have is I'm going to have a circle like this, and I'm going to have a cardioid like this. Okay? Now, the cool thing about this is no matter what the size is, I have to have 3 intersection points. I can draw this a little bit bigger to really emphasize that. So we have a circle, and we have a cardioid, right? So pole, here, here. Gonna have 3 intersection points, okay? Great, so we're gonna have 3 intersection points. In fact, I know one of these is the pole, because this by definition passes through the pole and a cardioid touches the pole. So one of my points is gonna be 0, 0. Now, the reason that's important is because the math is not going to give us 0, 0 as a possible solution, okay? Now, why? Well, let's think about that. If I take 0, 0 and plug it back in, I get 0 equals cos theta, I get 0 equals 1. What? That doesn't make any sense. So remember that for polar, if I have r equals 0, that defines, that without knowing what theta is, it defines the point. The point is the pole. I can have any possible value of theta. It does not matter. And no matter what, if r is 0, then my point is the pole. Okay? So we do need to solve this to get the other 2 solutions, right? The other 2 intersection points. So we say cos theta is equal to 1 minus cos theta. And then we add cos theta to both sides. I get 2 cos theta equals 1. So then cos theta equals 1/2. And we end up with the same solution as last time, where theta is going to be equal to pi over 3 or 5 pi over 3. But this time we're going to take this and plug it back in. So we're going to say r equals cos pi over 3 to get our first value of r. That's going to be equal to 1/2. We do the same thing for 5 pi over 3. And we get 1/2 as well. So our solution set, our full solution set for this, okay, is going to be 0, 0. We're going to get 1/2 pi over 3 and 1/2 5 pi over 3. Okay? So that's our solution set. And the reason we really need to use the graph here is we need to use the graph to get one of the solutions, to get this 0, 0 solution, because the math didn't give it to us because of the kind of quirkiness of polar coordinates. Okay? So let's look at method 3. Method 3, and you can do this method no matter what. You won't always want to because it can be kind of gross, but you can always convert to rectangular or Cartesian, solve, then convert back to polar. Okay? So let's take r equals 2 cos theta and r equals 1 plus cos theta. Okay? Now, maybe if you have a really good understanding of limacons, you can actually predict how many intersection points there are going to be. But if I look at this, a motivation for converting it to polar to rectangular is if I were to graph this, right? I have a circle of diameter 2 like this. And then I have a cardioid, which could be like this, or it could be like that, touching at 1 point, or it could be like that, touching it at 2 points, or I guess 3, right? So either it completely goes around the circle and the only intersection point is the pole, or it goes close to the circle, hugs it tight, touches it here, and then there's 2 intersection points, the pole and this point over here, or it goes like this and it crosses twice over here, and you end up with 3 intersection points, the pole and those 2. So because I'm not sure, let's say I'm just not very confident with how wide this limacon is, I'm going to convert this to rectangular, and then I'm going to use that to solve the system. So converting this to rectangular, I'm going to have, thinking back to my ratios, r is going to be equal to 2 times, and cos theta is equal to just x over r, right? If you think back to our triangle in our conversion where we have x equals r cos theta, right? So then cos theta equals x over r. So I'm going to write r equals 2 x over r. Multiply everything by r. I get r squared equals 2x. R squared is equal to x squared plus y squared. So I have x squared plus y squared is equal to 2x. And then for my other equation over here, I'm going to do the same thing. I'm going to say r equals 1 plus x over r. Multiply everything by r. I get r squared equals r plus x. Make my substitution. I have x squared plus y squared equals the square root of x squared plus y squared plus x. Now, once we're here, what do we do? Well, you can set them equal and solve. I'm going to kind of do one extra step. What I'm going to do is I'm going to say, okay, x squared plus y squared is 2x. So this is 2x equals the square root of x squared plus y squared. Well, if this is equal to 2x, then the square root of that must be the square root of 2x. So I'm just going to write root 2x. Then I'm going to have plus x. This is much, much easier to solve. So I'm going to subtract x. I get x equals the square root of 2x. Square both sides. We get x squared equals 2x. And then we can subtract. We have x squared minus 2x equals 0. Factor out an x. You have x times x minus 2 equals 0, which means that x equals 0 and 2. Okay? So x is 0 and 2. And then we want to figure out what r is. So what I'm going to do is I'm going to take this. I'm going to plug it all the way back into the easy equation, this one over here. So if we say x equals 0, then what is y? So I'm going to get 0 squared plus y squared is equal to 0, or 2 times 0, right? So y equals 0. If I have x equals 2, I get 2 squared plus y squared equals 2 times 2. So this is a 4, this is a 4. I get, again, y equals 0. Which means my solution set for rectangular solution set is 0, 0, and 0, 2. Now, if I want to convert that, and what that means for our graph, right, is what we actually have is I have a circle, and I have my cardioid like that. So it really does just touch the circle here and touch the circle here. So at 2 intersection points. So if I want to convert this to polar, normally you'd have to take this, plug it back in, right? Because we want to convert to polar, so we have to say, okay, well I know that, r squared equals x squared plus y squared, and I know that theta equals the inverse tan, or the arctan of y over x. But in this case, it's a lot easier than that. 0, 0, if we want to convert to polar, 0, 0 in polar is simply 0, 0. And 0, 2 in polar, oh man, I'm sorry, this is 2, 0. I'm just stupid. 2, 0, so this is going to actually be in polar 2, and the angle is 0. Okay? Now, don't get used to thinking that this is always how it is, okay? It's not. You will often need to convert, actually physically convert back and forth. In this particular case, it worked out really nicely. If it's along the polar axis like that, then it'll end up being the same point. But if it's not along the polar axis, then you will have to actually do a conversion back. Okay? So this will always work, and because you're solving in Cartesian, you'll always end up with all of the solutions, which is pretty sweet. So let's go on to method 4. Get rid of all this junk. All right. So method 4, we're going to call the unit circle. We kind of use the unit circle to solve this. So let's say I have, for 4, r equals sine of 3 theta, and r equals cos of 3 theta, which means I have 2 rose petals, right? So what I have is, I get, let me draw it up here. One of my rose petals is going to look like this. And the other one, I'll do my best, is going to look like this. Man, this is tricky. Yeah, there we go. So we're going to have a bunch of intersection points. If you count them up, and if I drew it well, there should be 4, I believe. It's also possible that I just, drew this kind of poorly. So, yeah. Because this here isn't really an intersection point, right? This should go around and touch the pole. So there should be 1 here, and then 1 per petal. So 1, 2, 1, 2, 3, 4. We should have 4 intersection points. This one I actually drew reasonably well. This one not so much. This one also not so much. So 4 intersection points. And what we can do is I can say, set these equal. So I have sine 3 theta equal to cosine 3 theta. Divide both sides by cosine 3 theta. Okay? So what I get is I get tan of 3 theta equals 1. Now, once I have this, okay, I can solve this. I can say that 3 theta is equal to pi over 4 plus 2 pi n. Which would also be, if you want to do it in degrees, 45 degrees plus 360 degrees n. Okay? And going further, I have theta equals pi over 12 plus 2 pi over 3 n, or 15 degrees plus 60 degrees n. Which means that my values of theta, I can have 15 degrees. I'll just switch degrees for now. I could have 75 degrees. I could have 135 degrees. I could have 195 degrees. And again, we're staying between 0 and 2 pi. I could have 255 degrees. And I could have 315 degrees. Okay, and if I go any further, I cycle back to 15 degrees. My r, corresponding r that would go with this, is I would have root 2 over 2. I would have negative root 2 over 2. I would have root 2 over 2 again. Negative root 2 over 2. Root 2 over 2. And negative root 2 over 2. So some of these are the same, okay? This one and this one are the same. This one and this one are the same. And the last two are also the same. This one, and where am I going to draw my line? We'll say this one and that one are the same. Okay? Which means, really, we end up with a nice solution set of 0, 0, root 2 over 2, 15 degrees, or, pi over 12. You get negative root 2 over 2, 75 degrees, and root 2 over 2, 135 degrees. Okay? And those are our 3 intersection points along with the origin. So again, you do have to actually use the graph for this as well. So we're kind of combining techniques here where we have to recognize that it's going to intersect the pole. But then the other 3 points come from using, this kind of old-fashioned unit circle thinking to find the last 3 points of intersection to solve for values of theta. Okay, theta and r. All right, so that's another way you can do it. Now, there's also one more way. Okay, one more way to do it, and this way is particularly useful when you're worried about dropping solutions, when you're worried that the algebra is not going to give you a couple of solutions, especially if those solutions, so far, the one that's been missing has been the pole. Sometimes it will miss others. That's really bad. And that takes us to method 5. Method 5 is replace r theta with negative r theta plus 180 degrees. This seems like a weird thing to do, but the reason that we're going to do it is because even this in polar represents the same points, okay? But it gives us an algebraically different equation, which means it could algebraically have different solutions, and it can give us missing solutions. So suppose we have r equals 2 plus 2 cos theta, cardioid, and r equals 1 plus 3 sine theta, inner loop. Okay, so if I were to graph this, I would have something that looks like this. I'm going to have my cardioid here, and I'm going to have my inner loop, and we don't really know necessarily what this is going to look like, but I'm going to have my inner loop like this. Okay, and we could have any number of intersection points, who knows? okay? We're going to end up with 5, just so you know. So let's go ahead and solve this, okay? So the first thing we're going to do is we're going to say, all right, well, you know, the origin is certainly, the pole is certainly one of the intersection points. We can kind of start with that. That's going to be 1. And now let's find more. So I'm going to say 2 plus 2 cos theta is equal to 1 plus 3 sine theta. I'm going to collect like terms, and I'm going to get 2 cos theta minus 3 sine theta is equal to -1. And remember, you can use the fact that a cos x plus b cos x, the sine x, just to cut myself early here, b sine x is equal to c cosine of x minus d, right? Where, you know, cosine of d is equal to a over c, sine of d is equal to b over c, which means in this case you're going to have cosine of d. Well, you know, we should calculate c first, I guess, to use it. So c is the square root of a squared plus b squared. So that's going to be equal to the square root of 13 in our case. So we take this and we get 2 over 13, or sine d, we're going to end up with -3 over 13, root 13. And when we do this, we end up getting that d, I think these should be the same. This is, yeah, a is 2, yeah, no, yeah, b, okay, good. And then we get d equals -56.3 degrees once you account for quadrant and all that. So that's going to be your d, which means I can rewrite this now as one simple nice thing. Well, not necessarily nice, but I have cosine of theta plus 56.3 degrees equals -1 over root 13. Okay, or what I've done is I've already divided both sides by root 13. And that means that theta plus 56.3 degrees equals positive or negative 106.1 plus 180 degrees n. So theta equals -56.3 degrees plus or minus 106.1 degrees plus 180 degrees n. Once we, you know, do this and between 0 and 2 pi, theta equals 49.8 degrees and 197.6 degrees. And r that would go with this, if we go back and substitute, is 3.29 and 0.09. Okay? So we have found 2 intersection points. Okay? We found 3.29, 42.8 degrees, and we found 0.09, 197.6 degrees. But if we go back here, this limacon really should have at least 3 intersection points, and we suspect that we're missing some. And even if we're not, we can always just check to be safe, okay? So what we're going to do to check is we're going to actually do this replacement, okay? So I'm going to get rid of all of our work so far. I guess I can leave the 0, 0 there. And we're going to do this replacement. Now, we're only going to replace one of them. So I'm going to replace the first one. So I'm going to say that I have this, I'm going to turn into instead, -r equals 2 plus 2 cosine of theta plus 180 degrees. Once I do this, I turn it into r equals -2 plus 2 cosine of theta, right? So this is going to give me -r equals 2 minus 2 cosine of theta plus 180, right? If we shift cosine by 180 degrees, we flip the sign. So now I have this equation and this equation. These are different than what I had before. So now I say -2 plus 2 cos theta equals 1 plus 3 sine theta. Even though we have not changed the function, I've changed how the algebra is going to work out. Because now I'm going to get 2 cosine theta minus 3 sine theta equals 3 instead of 1. And then I have root 13 cosine of theta plus 56.3 degrees equals 3. And then theta is going to be equal to negative 56.3 degrees plus or minus, again, if we do out all the algebra, 33.7 degrees plus 360 degrees n. And r, so theta's, I'll just make some space below. So theta is going to be equal to 270 degrees and 337.4 degrees. And r, that corresponds with this, will be negative 2 and negative 0.15 degrees. Which means our final solution set is going to be equal to, 0, 0. We're going to have 0.09, 197.6. We're going to have negative 2, 270 degrees. We're going to have negative 0. Negative point, this shouldn't be a degree, so that's what's messing me up. Negative 1.5, this is an r, not a theta. 337.4 degrees. And what am I missing? Oh, 3.29, 49.8 degrees. Whew, okay. So those are the 5 different ways that techniques that you can use to solve systems of polar equations. Depending on the specifics of the polar equation, one way or another might be easier, more useful. Remember, you can always check it by converting it over to rectangular and then solving it that way. But all of these techniques will come in handy depending on which system you're trying to solve. Generally, if you go back and you look at the 5 different techniques here and you look at the equations we used it with, those will generally be the ones that you'll want to use it, right? So if you have like a circle and a limacon or 2 limacons or whatever, you can use the associated technique to solve it. So practice hard, and that's systems of polar equations.